0. All right. So I've been over this. It should mostly seem familiar. So we started out talking about the voltage divider, and we figured out how to tell what's the output. You finite total, and then you can then do the voltage drop across R2. And at the end of the day, you come up with the classic formula up there, but we also call it the no load because we noticed that, and we mostly saw it when we used the analog voltmeters, that things don't always work out the way we expect. So in this case, now that we're very sophisticated, when we see a voltage divider made of two 10K resistors, and now I'm giving it a 10K load, I would hope most of us now realize, oh, that's just not going to work out. Now, to figure out now what would be our new V out, we could add together R2 and the load resistor in parallel, and that works, but the thing is that you have to do that for every load that you put in. And so this is why this is new information, but you may have gathered the reason to do the Thevenin decomposition is so you don't have to do this every single time when you're wondering what load I can drive with this voltage divider. And so we do the Hunter S. Thompson gonzo journalism. We go to the answer first. The answer is to convert the voltage divider from the two resistors in series with a pickoff point, the V out, into one voltage and one resistor in series. And I remind you, that's like the battery model. That way, then and I told you in the beginning without proof that R Thevenin is R1 in parallel with R2 added together. And then once we have the Thevenin equivalent, we can just connect any load to it because then the load is in series and it's very simple. Oh, and this is just what is R Thevenin and what is V Thevenin. R Thevenin is the equivalent resistance and V Thevenin is the unloaded voltage. So this all should be familiar. You should already have it in your notes. And then I made the analogy, and in fact, it's not an analogy, it's a direct comparison. It's exactly the same as the model of a battery. And it's just a kind of happy coincidence that we can model a battery with an internal resistance. And remember, the voltage of a battery has to do with the materials it's made of, the electrodes and the electrolyte inside, and the internal resistance of the battery is determined by the size of the electrodes. So a AAA battery has a much higher internal resistance than a D battery. And the D battery is able to supply more current, right? And we went through that. And blah, blah, yeah, this is just, and we should all have these notes. That's exactly the same thing we've gone over a couple of times. And, right, so now, when we have our Thevenin equivalent, we put on the load, we use this standard equation, the terminal voltage, and we figure out what is going to be the voltage delivered to the load. And in this case, it's going to be 10 volts, and that may not be good enough. Oops. So anyways, the steps are for a simple voltage divider is that the V Thevenin is the no load voltage, and the R Thevenin is the two resistors added in parallel. That's our basic recipe. So now I just want to go through the general definition of Thevenin, or at least Not completely general, but it just shows you a little bit more. It just fleshes the concept out. So I lifted this right out of Wikipedia, and yeah, I want to know. I got interrupted a couple times before I got it. I was going to print out some of these diagrams for you, but these 4 diagrams are going to use only in the next few slides. So the first one, if you're interested in writing down, is 1 and 2. So I'll make them bigger if you maybe you want to write them in your logbook. So if we look at this network, we can determine what is the output voltage. And the key here is that R1 does not, in this particular circuit, R1 does not participate. So to get the I total here, is equal to V1, that's what we're calling the battery, the 15 volts, and it's R4 plus R3 plus R2. Notice we're not doing any voltage divider equation. We can, I'll show you that in a minute, but the brute force way is to get, just as any other circuit, or the original way we looked at the voltage divider, is to get, and notice that R1 is not in that circuit because there's no current can flow through R1 because it's the open, so-called open circuit voltage, which is also when we use an ideal voltmeter. Now one thing you could notice though, which is convenient here in this particular case, is that you can put an equivalent resistance here, R23, which happens to equal 2K. So then you notice that you have a voltage divider with 2K and 2K, so you know, of course, it's 15 volts here because it's the output of the voltage supply, and V out here is going to be half of that, 7.5 volts, because you have a voltage divider made of 2 equal resistances. This is the physical intuition you develop over time. And because R1 is with the open circuit doesn't participate, it means that it's 7.5 volts over here too. There's no voltage drop across R1 in this case for the open circuit because there's no current through R1. So far this is nothing special. It's not different than what we were taught to begin with. We were told to get a V Thevenin of a circuit, it's the open circuit voltage, period, right? Now we're just seeing it in a little more generalized sense, and I do this something similar in 2200 where I do add R1 into that battery circuit. It gives people a little bit of confusion that if I measure it at the junction of R4 and R3, you don't have an issue with 7.5 volts. But when I measure at A, some people have a little issue that why is it it's still 7.5 volts at A when I have R1 there? And again, the answer is that we're assuming that our voltmeter has infinite input resistance or input impedance. Okay, and for the even with 1K resistors, our digital voltmeter has an input resistance of 10 mega ohms, so it's easily very high. Okay, so what's next? Unless people want me to wait a minute. Good? All right. Okay, now, the next step is that we write into the circuit all the equivalent resistances, or what, or not exactly equivalent, but what is the internal resistance of everything? Now, because we're assuming that the power supply is ideal, which they are to most degree, we simply put a wire there because R equals 0. That's a little different now. An ideal voltmeter has an infinite input impedance. An ideal power supply has a 0 output impedance. Current through, if you like. So it can supply all the current necessary so that no matter what circuit you put on it, it's going to give you 15 volts. Which they do. Remember, we could test it somehow. At some point they run out of gas, but they're not like batteries. Remember, I drew it up there. The terminal voltage of a power supply is flat-topped until you reach some current where it just can't supply it anymore, and then the output voltage just crashes really quickly. So for our purpose, that means that we draw a wire there instead of the power supply symbol. And now, once that's there like that, and just tell me if you want me to go back, if you're sketching that picture. Anybody want me to go back? I mean, I don't mind waiting while you sketch it in your logbooks, guys. I mean, I'd rather wait while you sketch it than, take pictures, but, sir, question?
Is it that we're literally placing a wire there, or?
Yeah. Well, not in the real, no, just mathematically. We could, but we don't have to. Sir?
Why is the 7 next to the red?
That's a good question. I don't know. I think it's, because remember, it's from up here. Yeah, it's the 7 from.
Oh, got it.
Yeah, I'm sorry. What I usually do is I copy paste it into a Microsoft Paint and erase things like that. I missed that one. I'm sorry. Pay no attention to the 7 on the right side. Now the red 2K, you take my word for it for the moment, but I'm going to show it to you in a minute. Okay, so now there's the equivalent, but what happens is then you got, it's easy to draw squiggly lines, I suppose, R4, and we have R3 and R2. So now that's point B. And then this is point A. Now there's mathematical proofs behind this, and I just lifted this right out of Wikipedia, the words and the diagrams, so if you're interested, you could go there. So remember, whenever we have a network, we drill down, and in this case, we want to convert this to R4, and combining R2 and R3, and that's going to be equal to 2K because they're in series. I'm skipping steps. Is everybody okay with that? Now, this one is 2K also equals 2K, and that's nice because then we know that R2, 3, 4 equals 1K. As we add together two 2K resistors in parallel, we get 1K. And then we have R1 still here equals to 1K. So then we conclude then, therefore, or this implies, equal sign greater than, that R total equals 2K. And there it is. So we end up with the voltage source, which is the open circuit 7.5 volts, ideal voltage source, in line, in series with a 2K Thevenin resistor. So again, it's not a lot different than what we've already know, but it's just a little more formalized now. So once you attach a load to this circuit, R1 becomes a factor. It's not surprising, I hope. Now, Hayes goes through some explanations about why R1 and R2 are added in parallel, and I just still can't wrap my head around it. But as I was telling a few of our colleagues about an hour or so ago, if all else fails in physics, just go back to the math. And if I accept Thevenin, that means that and remember this circuit here, this is drawn because it's easy, right? But what's really here is that we have our V in and we have our R1 and we have our R2, and then it comes back, right? And this is out, and this is out. We could call it AB again. If I replace V in by a wire, then I have this. And notice that if you can do a little topology, changing shapes in your brain, R1, R2. See, electrically, I'm basically just taking this B, because there's a zero resistance path here, I can just take this B and slide it to here. And I can just let this wire here stretch a little bit and shrink this wire, and then I come to that. And now you see how R1 and R2 add in parallel. I haven't proved it, but I've shown you that I've got this Thevenin decomposition that I know works, and when I apply the rules, the strict rules of Thevenin, you see how R1 adds in parallel with R2. It's counterintuitive because R1 is attached to the voltage supply and R2 is attached to ground. But of course it is much easier when you draw it this way. I'm still trying to, he offers throughout the book really strange reasoning processes that I can't follow. I've tried very hard. He's a nice guy. I've never talked to him, but I've exchanged emails with him, and he's very generous. Of course, you may not feel like that because all your homework, he gave me all those homework assignments. All right, let's see what I got. Oh, does anybody need me to slow down? Want to keep? I'll publish this too. All right, let's see what I got here. Right, so at the end of the day, your voltage divider becomes what you see on the right. R Thevenin is R1 in parallel with R2, and V Thevenin is V out, which this is the classic voltage divider equation, R2 over R1 plus R2. And we're going to be using this over and over again. Yeah, and in fact, if I asked you to write some notes down from chapter 1. You may, well, this is from Wikipedia. The next slide comes from Hayes. So he wanted you to do an exercise where, excuse me, that's 1 meg, this is 1 meg, and let's see, 100K, 100K, and then 10K, and 10K. And we did something like, in a way, we did something like this in class when we when we used the digital and we used the analog voltmeter. So this one would have an R Thevenin equal to 5 meg, oops, capital M, and then this is 500K, this is 50K, this is 5K, and this is 500 ohms. So if we were using the digital voltmeter, even the digital voltmeter might have trouble with this one, because we got a voltage source with a 5 meg ohm resistor here. And now we're going to put, if we put the digital voltmeter here with 10 meg ohms, that might be too much of a load. But of course, once you get to 500K, 50K, 5K, no big deal. The analog voltmeter the R analog equals only 10K. So in that case, the only circuit I could measure would be this one here, because the rule of thumb is the 10 times rule. So we want the input impedance of the next stage to be 10 times the we want the input impedance of the next stage to be 10 times the output impedance of the stage before it. Okay, so what goes on is that the analog voltmeter needs enough current for this coil, whereas the digital voltmeter just has a circuitry here, and it basically has a capacitor here and a resistor in feedback. We're going to learn about this. And it charges the capacitor, and then it measures the time constant, which we're going to do hopefully today. I'm going to show you how to do that in a few minutes. It measures the time constant of that RC circuit. And and not only that, it measures the voltages and the change over the RC, because the RC is fixed by the value. So it has some way of counting and converting the time into a voltage reading. But the input impedance is quite high. It turns out we're going to play with these op amps. Their input impedance is infinite. But in this configuration, the input impedance is going to be this feedback resistor. So in this case, it would be 10 meg ohm. It makes no sense to you right now, but you'll know what that means eventually. The most important thing is that the R of a DVM is about 10 megs. All right, what's next? Oh yeah, so a little digression. What does ground means? It turns out I goofed. This is actually not an earth ground. That's just analog ground, they call it, I believe. Let's see. Local ground. Okay, return ground. And there's this, you notice that's why they add these wires on the right, because on the left side, these are just common connection point. It doesn't necessarily mean earth ground. So earth ground is something we always have to worry about, because in our case, our oscilloscopes and our function generators are earth grounded. So the black wire from them is always held at 0. It can be a pain in the butt. And so you see here that the earth ground's not attached. Here, we've defined this as the local ground because we want that to be 0, but there's no need to do that. So anyways, I guess that's why then we segue into this. Well, not segueing, that was a digression. So the rule of thumb is that R out for A has to be less than or equal to 1/10. So this has to have 10 times greater than or equal to 10 times R out for A. And if you do that, that means that you're basically going to get the output voltage that you predicted when you built the voltage divider in the first place. And I don't know if you can see that. This is the crappy illegal PDF I have of the manual. So, then I can't write on it. Wait a minute though. I can make it bigger though. Let's try this. How's that? A little better. So, let me try redrawing it. Okay, so circuit fragment A, they call this in A. So we have, and they're calling it R. And another R. This is out of A. Now we're taking that into B, and even saying that B is another voltage divider. In fact, what these can be is amplifier stages as well. But we can still treat the amplifier stages as voltage dividers. That's why I'm emphasizing that we need to learn this, so why it's so important. So one thing that is not entirely clear in the text is that the input of B, so the input impedance of B is equal to, in this case, 20K. So it's R1B plus R2 in series, because it's going to ground, and then we're assuming at the moment nothing's attached to B. So that means then that the R out of A has to be less than or equal to 2K. You see that? So the input impedance of B is 20K, because and in fact, if we follow this rule, all right, so right now we assume nothing's attached to B, because we don't want anybody to be worried, because you're going to say to yourself, well, if I have a load attached to B, don't I care about that load? And I'm telling you right now, you don't. There's nothing attached to B. So B represents to A load going through the two resistors into ground, right? You see that? Because it's a pathway for current. Well, I guess people don't want to admit they don't understand something. Let's assume for a minute. Let's see if I can make this happen. All right. So we have some voltage divider. We know that it has an output voltage that's, and why don't we label these guys to make it easier to refer to them. And so V out over V in for A is equal to R2A over R1 plus R2. We also know that the R Thevenin equals to R1A added in parallel to R2A. Okay? Now, I'm telling you that I'm going to hook up two resistors like so. And we see that because I have those ground symbols, which is basically the return to the power supply, that I have a current path. So current is going to flow from the output of A into the B and down to ground. And the amount of that current is going to be proportional to the voltage at A out divided by the total R, which in this case is R1 plus R2. So the input impedance of a voltage divider is simply summing the two resistors. So it's a load. And yes, in principle, if B was attached to something else, we might have to add that into the load. Because B is, if I put a load on the output of B, B has to drive it. But B is being driven by something before it as well, and not of an ideal source. But for now, we don't want to think about loading B. We just want to look at A and B is a load on A. So we need the input impedance of B to be 10 times the output impedance of A. So we determine that B is at 20K input impedance. So that means then the output impedance of A has to be less than or equal to 2K. So then that means that the two R1 and these two guys have to be less than or equal to 4K, because when I add them in parallel, I'm going to get 2K. So now I've satisfied the 10 times rule. Okay. And let's see here. This one come out. I enhanced this one. So he does a calculation in the book, and so some of us might have been saying, "Well, crap. When I hook up a load to B, do I have to go back and recompute the input impedance of B? Because in principle, the load on B will affect the input impedance, because in principle, if I had a load here of 10K, for example, then this would become 5K lowered down, and then the input impedance of this thing would become 15K instead of 20. But if we follow, when we design circuit fragment C, if we follow the 10 times rule, then we know that, and remember, this, now you understand why we have one of the rules of thumb. If this now is 100K, and in fact, what is it that we wanted? This is going to be 5K. So then this has to be, all right, come on, I'm getting tired. Yeah, if this was 50K, now let's leave it for 100K for now, just because it's more obvious. Because we have these two resistors in parallel, we can ignore the 100K resistor. That's the whole point of it. So as long as the load is 10 times greater than the output impedance, then I don't have to bother with adding it into the calculations. So then that means that since these two 10Ks were fixed, we're given these as two 10Ks, then we knew that we had to have two 4Ks here, because then this has an R out of 2K, this has an R in of 20K. We're good, right? This has an R in of 50K, and this has an R out of 5K. So as long as we always follow the 10 times rule, we don't have to worry about what's going on in previous stages. We just worry about the relationship of any two stages. I think that's it. I got a couple more slides here. Yeah, those are just extras. Okay. All right, so why don't I'll stop this recording and I'll save this. We'll take